Hi, welcome to the fifth and final video for the chapter Real Numbers. So in the previous video we were looking at irrational numbers, and in this video we are going to look at rational numbers and their decimal expansions. Now you have learned in smaller classes that rational numbers will have either a terminating decimal expansion or a non-terminating repeating decimal expansion. Let's see what that means. Consider two rational numbers, 2 by 5 and 2 by 3. If you try to find out the decimal expansion of 2 by 5, you just need to divide 2 by 5, and if you actually perform the division you will get 0.4. Okay, so 2 by 5 can be written as 0.4, which is a terminating decimal. So this is an example of a terminating decimal expansion. Now if you look at the second rational number 2 by 3, if you divide, you'll find that this decimal expansion is non-terminating and repeating. So you'll get 0.6666 and so on. So this is an example of a non-terminating repeating decimal expansion. So these are the two types of decimal expansions possible for rational numbers. Now in this video we are trying to find out, just by looking at a rational number p by q, we'll try to determine whether it is a non-terminating repeating decimal expansion or a terminating decimal expansion. First let's consider a few rational numbers that have a terminating decimal expansion. For example 0.375. So you know that this is a terminating decimal expansion. Now if you try to express this in p by q form, you know that 0.375 can be written as 375 divided by 1000, which is equal to 375 divided by 10 to the power 3. So that's the p by q form for 0.375. Let's look at another example, 0.104. This is another terminating decimal, and this can be written as 104 divided by 1000 or 104 divided by 10 raised to 3. So the obvious thing here is that if you have a terminating decimal expansion, you can straight away write it as one number divided by a power of 10. So let's just look at another random example. If you have a number like 0.56, you can write it as 56 divided by 10 squared. Now let's explore this fraction further and see if this can be simplified. We can write 375 by 10 raised to 3 is equal to 3 into 5 cubed divided by 10 is 2 into 5. So 10 cubed is 2 into 5 cubed. That's 2 cubed into 5 cubed, which is equal to 3 divided by 2 cubed. If you simplify the second fraction 104 divided by 10 cubed, you can see that this can be prime factorized as 13 into 2 cubed divided by 2 cubed into 5 cubed, which simplifies to 13 by 5 cubed. Let's look at a third example, 3.65. 3.65 can be written as 365 divided by 100, and this can be simplified to 5 times 73 divided by 2 squared into 5 squared, which is equal to 73 divided by 2 squared into 5. Now if you look at the three simplified fractions, this one here, this one and this one, what do you observe? We find that in the denominator you'll either find a power of 2, like in this case, or a power of 5, or you'll find both, a power of 2 multiplied by a power of 5. To summarize, if you have a terminating decimal expansion, you can write it as a fraction in p by q form with all the common factors cancelled out, in such a way that q is of the form 2 raised to n into 5 raised to m. You can write this as a theorem in this way. So a rational number with a terminating decimal expansion can be expressed as p by q, where p and q are co-prime, and the prime factorization of q is in the form 2 raised to n into 5 raised to m, as we just saw. Two things to note here. First, here it says where p and q are co-prime. So first you need to cancel out the common factors. And another thing to note here is n and m are non-negative integers. So what does non-negative mean? It can be positive or 0. So if it is 0, for example, if n is 0 in 2 raised to n into 5 raised to m, if n is 0, that means we'll only have 5 raised to m. So we'll only have a power of 5 in the denominator, like we saw in this example here, this one. And if m is equal to 0, this will reduce to 2 raised to n. That means we'll only have a power of 2, like we saw in this case. So that is the case when the decimal expansion terminates. What about the converse of this theorem? So now we have seen that if the decimal expansion terminates, then the denominator can be expressed as 2 raised to n into 5 raised to m. What about the opposite of this? That is, if the prime factorization of q is of the form 2 raised to n into 5 raised to m, then we can say that the decimal expansion will terminate. Let's look at a few examples to see how this works. Consider the rational number 3 by 8. Now 3 by 8 is the same as 3 by 2 cubed. So here it's a case where the denominator is expressed in the form 2 raised to n into 5 raised to m. Now to prove that the decimal expansion of this rational number 3 by 8 is indeed terminating, we need to multiply both sides of this fraction by 5 cubed. So if you do that multiplication, this becomes 3 times 125 divided by 10 cubed, which is 375 divided by 1000, and that's equal to 0.375, which is a terminating decimal. Let's look at another example. If you have a rational number like 7 by 80, this can be written as 7 by 16 times 5, which is 7 by 2 raised to 4 into 5. So here it's an example of a rational number in which the denominator can be written in the form 2 raised to n into 5 raised to m. Now is this a terminating decimal? To express this as a terminating decimal, we multiply both sides by 5 cubed. So you can write 7 into 5 cubed divided by 2 raised to 4 into 5 cubed, which is 7 into 125 divided by 2 raised to 4 into 5 raised to 4, which is equal to 875 divided by 10 raised to 4, or 0.0875. So the idea here is to multiply by a power of 5 or a power of 2 in such a way that you get equal powers of 5 and 2 in the denominator. So if the denominator is, say, 2 cubed, then you have to multiply both the numerator and denominator by 5 cubed. So this becomes, the denominator finally becomes 1000. Then you can just divide the numerator by 1000 to get a terminating decimal. Now let's look at the other case, that is when the decimal expansion is non-terminating and repeating. In such cases, you will find that the denominator of that rational number cannot be expressed in the form 2 raised to n into 5 raised to m. If we state it as a theorem, if p by q is a rational number such that the prime factorization of q is not of the form 2 raised to n into 5 raised to m, then x has a decimal expansion which is non-terminating and repeating. So if p by q is a rational number and the prime factorization of q is of the form 2 raised to n into 5 raised to m, then the decimal expansion is terminating. And if the prime factorization is not of the form 2 raised to n into 5 raised to m, then the rational number is non-terminating, repeating. And with that, we have come to the end of the chapter. Thanks for watching.